This is the first module of two from chapter 9, Electrons in Atoms in the Periodic Table. So by the end of this model, you will be able to understand and explain the nature of electromagnetic radiation. Also, you will understand and explain the key characteristic of the Bohr model of the atom, understand and explain the key characteristic of quantum mechanical model of the atom, and predict the relative wavelength, energy, and frequency of different types of light. So, on May 6, 1937, while landing in New Jersey on its first transatlantic crossing, the Hindenburg burst into flames, destroying the airship and killing 36 of the 97 passengers. Apparently, as the Hindenburg was landing, leaking hydrogen gas ignited, resulting in an explosion that destroyed the airship. The skin of the Hindenburg, which was constructed of a flammable material, may have also been partially to blame for its dismiss. The Hindenburg was filled with hydrogen, a reactive and flammable gas. So the question is, what makes hydrogen reactive? Mother blimps are filled with helium, an inert gas. The nucleus of the helium atom has two protons, so the neutral helium atom has two electrons, a highly stable configuration. In this chapter, we'll learn about models that explain the inertness of helium and the reactivity of other elements. What is what is it about helium atoms that makes helium gas inert? By contrast, why is hydrogen so reactive? Elemental hydrogen exists as a diatomic element. Hydrogen atoms are so reactive that they react with each other to form hydrogen molecules. What is it about hydrogen atoms that make them so reactive? So here we have a helium atom. We have here the nucleus with the two protons, and there's orbit with two electrons around that nucleus. For hydrogen, we just have one proton in the nucleus and one hydrogen in that orbital. So if we have two hydrogens atoms, that means that somehow if they can share both electrons, they will have two for each one, or something like this. So that will explain why hydrogen, you're going to find hydrogen as a molecule as H2, because they are sharing those two electrons, and now as well as helium they have two electrons. That's why you have the molecule of H2 of hydrogen. And most of the time you're going to find helium as just one atom. You're not going to see helium 2. So models to explain the inertness and reactivity of elements. Are other elements as reactive as hydrogen? The reactivity exhibited by hydrogen is also seen in other group 1 elements, such as lithium and sodium. The inertness of helium is seen in neon, argon, and the other noble gases. Mendelev's periodic law sums up these observations. When the elements are arranged in order of increasing atomic number, certain sets of properties recurs periodically. Models and theories help explain the observed behaviors of groups of elements such as the group 1 metals and the noble gases. So, we're going to examine two important models, the Bohr model and the quantum mechanical model, that propose explanation for the inertness of helium and the reactivity of hydrogen and the periodic law. These models explain how electrons exist in atoms and how those electrons affect the chemical and physical properties of elements. Niels Bohr, that is this guy in the left, and Erwin Schrödinger, this one in the right, along with Albert Einstein, played a role in the development of quantum mechanics, yet they were bewildered by their own theory of wave-particle duality for the electron. So, electromagnetic radiation, the interaction of light with atoms help to shape scientists' models of the atom. The light is a form of electromagnetic radiation. Light is a type of energy that travels through space at a constant speed of 3.0 times 10 power of 8 meters per second, or 186,000 of miles per second. Light has properties of both waves and particles. So, when a water surface is disturbed, waves are created that radiate outward from the side. The wave carries energy as it moves through the water. So, these waves are created by that disturb in the surface, and those waves have also energy. So, in the electromagnetic radiation, we have wavelength. The wavelength of the light is also known as the lambda, using this symbol, okay, lambda, is defined as the distance between adjacent wave crests. So when you have radiation like this, you can measure the distance from this crest to this crest, and that's the wavelength. Also, you can measure the distance from here to here, and has supposed to be the same for the same radiation. So you can measure from this point to this point, from this one to this one, or also you can measure from here to here. This is the crest and this is the crest, so the distance from here to here is the same as this one. So that's the wavelength. The color of light. White light, as produced by the sun or by a light bulb, contains a spectrum of wavelengths and therefore a spectrum of color. We see these colors, the red, the orange, the yellow, the green, the blue, the indigo, and the violet in a rainbow, or when white light is passed through a prism. And also this is known as the visible spectrum. Red light with a wavelength of 750, around 700 here, nanometers, has the longest wavelength of visible light, while the violet light with a wavelength of 400 nanometers has the shortest wavelength of the visible light. So from here to here, the wavelength is increasing from the left to right in this graph. And the red here has the longest wavelength, around 700, while the violet has the shorter wavelength of the visible spectrum with a 400 nanometers. The presence of color in white light is responsible for the colors we see in our everyday vision. For example, the component of the white light, if you go through a prism, as we can see here, and I know that most of the time, and also when it's raining and you can see the rainbow, you will see the components of the white light. Okay, so you can see all the colors from red, orange, yellow, green, blue, indigo, and violet, all of them. And when it passes through that prism, showing all the components or the components of colors that are part of the white light. A red shirt appears red because it reflects red light. The shirt absorbs all of the other colors of light except the red light. So when you see a piece of cloth or anything that has color, that means that that material absorb all the other color with the exception that the one that you can see. So our eyes see only the reflected light, making the shirt appear red in this case, and this girl on the beach. So whenever you see like a blue jean, is because that material absorb all but the light but reflect just the blue. Now going back to electromagnetic radiation, there's another definition, is the frequency. The frequency of the light, also represented by this V is known as nu, is defined as the number of cycles or crests that pass through a stationary point in 1 second. Wavelength and frequency are inversely related. The shorter the wavelength, the higher the frequency, and as well, the larger the wavelength, the shorter the frequency. Okay, so they are inversely related. As longer the wavelength, smaller the frequency. So let's see this example. Here we have one radiation like this, okay? And let's assume that this is 1 second from here to here. This is the wavelength from here to here, and from here to here, from here to here. So this distance is the wavelength, and we have here another frequency. And as we can see here, the wavelength is shorter. Okay, so from here to here, this distance is shorter than this one. So this radiation has a shorter wavelength than this one. Now, we mentioned that from here to here is 1 second. So how many cycles are in this um, radiation? Starting from here, this is 1, this is 2, this is 3, and this is 4 cycle in 1 second. Now, taking this example, we have 1, we have 2, we have 3, 4, 5, 6 cycles. Or also we can count the crest. 1, 2, 3, 4, 5, 6 crest. 1, 2, 3, 4. So as we can see, as shorter the wavelength, higher the frequency. We have 6 crests here and 4 crests here. So this has the long wavelength, short wavelength, but this one has lower frequency, while the shorter wavelength has the high frequency. So that's the inverse relation between the wavelength and the frequency in electromagnetic radiation. Now, light can be viewed as a stream of particles. A particle of light is called a photon. We can think of a photon as a single packet of light energy. Okay, so a photon is basically the simplest way to see light energy. It's just like the basic unit, let's say that way. Okay, photon is the basic unit of light energy. The amount of energy carried in the packet depends on the wavelength of the light. The shorter the wavelength, the greater the energy. So if it's shorter the wavelength, that means that the frequency is larger. So as higher the frequency, greater is also going to be the energy. Okay, so as shorter the wavelength is greater the energy, as higher the frequency is greater the energy. So if we have a lower energy, that means that it has a lower frequency but a larger wavelength. Light waves carry more energy if their crests are closer together. That means that has a higher frequency and shorter wavelength. The violet light, that is, has the shorter wavelength of the visible region, carries more energy per photon than the red light, because the red light has a longer wavelength, longer wavelength. So that means that has a shorter frequency. Okay, so the violet has more energy than the red light. So to summarize, electromagnetic radiation is a form of energy that travels through space at a constant speed of 3.0 times 8 power to 10 meter per second and can exhibit wave-like or particle-like properties. The wavelength of electromagnetic radiation determines the amount of energy carried by one of its photons. The shorter the wavelength, the greater the energy of each photon. Remember that shorter wavelength means that your frequency is going to be higher. So as higher frequency, greater the energy. That's the relationship between them. And the frequency and energy of electromagnetic radiation are inversely related to its wavelength. Okay, so frequency and energy are directly related, while when you compare them with the wavelength, is inversely related. As you have a higher frequency, higher energy, but the shorter wavelength. Or lower frequency, lower energy, and larger wavelength. So let's talk about the electromagnetic spectrum. The entire electromagnetic spectrum with short wavelength, high frequency radiation on the right, and the long wavelength and low frequency radiation on the left is shown here. Visible light is a small silver sliver in the middle. So here we have the whole electromagnetic spectrum, this wavelength. So this has at the left the larger wavelength. As this one is the shorter wavelength. So that means that if this is the higher wavelength, the frequency is going to be the shorter. Okay, so you're going to have less energy than comparing to the gamma rays. The gamma rays are the ones with the shorter wavelength, so that means that has a higher frequency and high energy. Okay, so from the energy is going to increase from left to right when we have here the longest wavelength and here the shorter wavelength, And also the frequency is going to increase from left to right, and the wavelength is going to decrease from left to right. Okay, so here we have all the different electromagnetic spectrum and radiation. We're going to talk a little bit from each of them in the next few slides. And here we have the frequency. We can see here the longer the wavelength, shorter the frequency. Here is the shorter wavelength, so we're going to have a higher frequency. Low energy and high energy. So let's start with the gamma rays. The shorter wavelength and most energetic photons are those of gamma rays. The gamma rays are produced by the sun, by stars, and by certain unstable atomic nuclei on Earth. Excessive human exposure to gamma rays is dangerous because the high energy of gamma ray photons can damage biological molecules. Okay, so the gamma ray, they have the shortest wavelength, also the high frequency, as we can see here in the top, as the frequency is increasing from right to left, the wavelength is increasing from left to right. Okay, so the energy also is increasing to the left. So that's why the X-ray, the gamma rays are the ones with higher energy and higher frequency as compared to the rest of the electromagnetic spectrum. The next is on the electromagnetic spectrum is the X-ray. This has longer wavelength and lower energy than the gamma rays, and they're familiar to us from their medical use. X-rays pass through many substances that block visible light and are used to image internal bones and organs. Like gamma rays photons, X-ray photons carry enough energy to damage biological molecules. While several yearly exposures to X-rays are relatively harmless, excessive exposure to X-rays increases cancer risk. So between X-rays and visible light in the electromagnetic spectrum is the ultraviolet or UV light, familiar to us as a component of sunlight that produces a sunburn or a suntan. While not as energetic as gamma ray or X-ray photons, ultraviolet photons still carry enough energy to damage biological molecules. An excessive exposure to ultraviolet light increases the risk of cancer and cataracts and causes premature wrinkling of the skin. The fourth group is the visible light that ranging from the violet to the red. Remember that the violet has a shorter wavelength. Okay, and the um, frequency also has a higher energy, higher frequency as compared to the red. So the red one has a longer wavelength, and we are increasing from left to right the wavelength. So that's why we have the red here and the violet in the left inside this visible light region. The photons of visible light do not damage biological molecules. Photons of visible light do cause molecules in our eyes to rearrange, which sends a signal to our brains that results in visions. Infrared light is next with even longer wavelength than visible light. So that means that they have less energy than the visible region radiation. The heat you feel when you place your hand near a hot object is the infrared light. All warm objects, including human bodies, emit infrared light. So that's why, while infrared light is invisible to our eyes, infrared sensors can detect it and are often used in night vision technology to see in the dark. The infrared region of the spectrum warms objects, such as human bodies, glow much as a light bulb glows in the visible region of the spectrum. So here we have the comparison between a normal photograph in the left and the infrared photograph in the right. Okay, so the warmest areas appear as red, as we can see here, the dog, okay, the face of the man, and the hands and the legs. But also we can, in this picture, as you can confirm the familiar idea that healthy dogs have cold nose. We can see here the blue nose of this dog and this one, because they don't emit that UV radiation. So that means that those spots in the dogs are cold than the other parts of the dog. So This is with the infrared radiation. The next one is the microwave. Beyond infrared light at longer wavelengths still are microwaves used for radar and in microwave oven. Microwave light has longer wavelengths and therefore lower energy per photon than visible or infrared light. Microwave light is efficiently absorbed by water and can heat substances that contain water. Substances that contain water, such as food, are warmed by the radiation of a microwave oven, but substances that do not contain water, such as a plate, are not. Some types of dishes contain substances that absorb microwave radiation, but most do not. And finally, the longest wavelength of light are the radio waves, which are used to transmit the signal used by AM and FM radio, cellular phones, television, and other forms of communication. So this type of radiation is used basically for communication in from the electromagnetic spectrum. So take 1 minute and arrange the three types of electromagnetic radiation: visible light, X-rays, and microwaves in order of increasing wavelength, frequency, and energy. So let's continue. Chemistry and health radiation treatment for cancer. X-rays and gamma rays are sometimes called ionizing radiation because their high energy in their photons can ionize atoms and molecules. When ionizing radiation interacts with biological molecules, it can permanently change or even destroy them. Doctors can use ionizing radiation to destroy molecules within unwanted cells, such as cancer cells. So, in radiation therapy, doctors aim X ray or gamma ray beams at cancerous tumors. The ionizing radiation damages the molecules within the tumor cells that carry genetic information, and the cell dies or stops dividing. Healthy cells are often inadvertently sustain damage during treatments, resulting in side effects such as fatigue, skin lesions, and hair loss. Doctors try to minimize the exposure of healthy cells by appropriate shielding and by targeting the tumor from multiple directions, minimizing the exposure of healthy cells while maximizing the exposure of cancerous cells. With this, we finish our first model of two from Chapter 9, Electrons in Atoms and the Periodic Table.